Hello, so today we are going to be doing some regression and hopefully learn some of it in the process. I'm going to be using R today because for regression I think R is good. If I do more videos in the future we can look at Python, but I'd like to pick the best tools for the job. So if there are more videos in the future, expect them to be in a different language or not. Okay, let's see how that goes. So we'll start off with getting data. Okay, so how to get data? Okay, so we'll get it from the UCI machine learning repository. Okay, here we'll go to data sets and we will go to regression. Okay, so I found this data set today. It's called airfoil self noise. Okay, so once we download this, I had downloaded this earlier. Okay, we will get a data set that looks like this. Okay, so you will see that this is just a bunch of numbers. Okay, there's no description. So knowing this is important for the first thing that we'll do in our code. Okay, so let's switch to R Studio. So I've written some code already before and we're going to be using that as a cheating, but most of the code we'll build along the way. Okay, so what I did was I took the data set and I have put it in the read table function. Okay, so what this is doing is it is taking the link of the data set and reading it directly from the web. Alright, we have a argument called header which tells that this data does not have a header. Okay, so headers will be essentially names of the columns that will be auto generated, and we are skipping none of the rows on the top of the data set. Okay, so how to get this link? To get this link, essentially we go to the data folder here. Alright, and this is the data file, so we copy the link address. Okay, and that is exactly what we have here. Okay, fine, so let's begin. Okay, so we have our data. Then what we can do is we can look at it and okay, control enter, and this gives us the view. All right, so there's no description. Okay, and we have started a regression exercise, so let's figure out what the data is about. All right, this is a fairly clean data set, so we'll not do a whole lot of EDA on it because this is a regression video. So we'll focus on doing regression, but nonetheless we look at what the data has, because that is the least amount of information that you need to do regression. Okay, so essentially this thing has 6 columns. Okay, and it is for essentially from a airfoil experiment. All right, so now what we're gonna do is we're gonna give appropriate names to our data set. Okay, so this is us just building our data set. So I'm going a little bit fast in this section. Okay, all right, so what we are supposed to predict, there's 6 things in this data. Okay, there's the frequency, angle, chord of the airfoil, velocity, displacement and pressure. All right, we saw that everything is numerical in nature. Okay, we'll talk a lot about this as we move on. Okay, so we're gonna be renaming these wonderful v1, v2, v3s with the proper names. Okay, and this is our prediction. Okay, this is the variable that we want to make a model for. Okay, so let's actually do that. Okay, once we have that, we can rename our columns. Okay, just like that. Okay, once we have that, we can have a preview of our data. All right, so we can see that. Okay, so let's try to one more thing. So we can look at the structure of our data. Okay, and this is what we get. So it tells us the primary thing to note here is it'll tell us the kind of variable are things that this column has. Okay, so this is an integer column and these are numerics. Decimals essentially are allowed. Okay, all right, this will be useful eventually. The other thing we can do is we can check the size of the data. Okay, oops, run that whole thing again. Okay, so this is essentially the number of rows and the number of columns. Okay, this should match, if you've pulled the data correctly, with this. Okay, all right, so our data pull is successful and we have named the columns properly. So now some EDA is in order. All right, so the next thing we'll do is we'll look at this data visually. Okay, so okay, so I don't really like these plots, but I'm trying to make a point here. Okay, so what is happening here is that on the diagonal you can see that every variable in our data set has been plotted against every other variable. So this plot is essentially a plot of frequency and angle. All right, and so for various angles in our data set, the frequency that is present has been plotted here. All right, and okay, our goal is to model pressure. Now we can see that there's a lot of grouping in this data. Okay, because in an experiment you have to choose the chord of the wing, chord length. All right, and that can only be a finite number of fixed values. So you can see that for every chord over here, okay, chord length over here, there's another angle setting that we have. That's why we have this, you know, a little more systematic looking plot. Same thing goes for, you know, for various angle settings. We have our velocity being measured. All right, so okay, so in this case we have essentially a lot of angles and a few velocities. Okay, so this gives us a general idea of what is happening in our data. All right, now we will move on to doing greater things. Okay, I still want to have a better clarity of our data set. So what we're going to do is we're going to look at these two variables at a time. Okay, on our y-axis, we'll plot the y-axis first. Okay, we care about modeling the pressure. Okay, so this will stay constant and we'll make a bunch of plots now. Okay, okay, let's begin with frequency. Okay, so this is a plot for various frequencies that were applied in this experiment. Okay, the pressure that was observed. You can see there is there's this pressure over here. In lower frequency regimes you have a variation in pressure. Okay, but okay, actually the whole point of this exercise is to build a model. So let's keep our subjective observations aside. Okay, and let's try to build linear regression. So I think it's important at this point that I tell you, you know, how I think of linear regression. All right, so if you're looking, okay, so there's this Newton's equation called F equals ma. Okay, m times a. All right, so this is an equation that relates, you know, the force with mass of an object and the acceleration that it is undergoing. All right, so this is an equation, most of us will know this. All right, and this is universally accepted. What an equation in this case is trying to do is it is trying to find a relationship between measurements that we can do. All right, so this is, we can measure the mass and acceleration of an object. All right, and if we combine it, we get the force applied on it. All right, so now Now the thing is, this is a universally known equation, all right, and essentially this is also a mathematical model. Okay, this is a model of the forces that work in the world, okay, in Newtonian mechanics. Similarly, we had the gas equations, PV equals to nRT. All right, over here also we're relating, for an ideal gas, the pressure, volume, the number of the amount of gas, okay, the gas constant, and temperature. All right, so essentially what an equation is trying to do is this equation is a mathematical model of an ideal gas. All right, it's trying to unify all its properties into a single mathematical expression. And essentially when we do data science, okay, we are doing statistical analysis, we are trying to come up with equations that combine things that we care about. All right, so right now there is no universal equation that relates these six things, okay, in the experiment, and that is the goal of our linear regression exercise, that we find a correct as possible, okay, relationship between these 6 variables that we observe in the world. Okay, because okay, in the F equals ma example, if I know mass and if I know the acceleration of an object, I can very accurately predict the force that was applied on it. All right, in the same spirit, what we are trying to do is we are trying to model pressure. Okay, we are trying to explain how pressure is affected by the rest of the 5 variables. Okay, so that is we are going to be looking at all the regression that we are going today from this lens. All right, so I have few more plots that I've written the code for. So again, this tells us, as we vary the angle, how the pressure being observed is distributed. And okay, let's do that. So what we can see here is that pressure is all over the place. All right, in every single instance when the angle is being changed. So we can't really say there's a direct relationship that we can discern between these things. Okay, then we are looking at the displacement parameter that was used in the experiment and the pressure that was observed. All right, and here also things are all over the place. There's no relationship that you can just have an opinion about just looking at this plot. Also, I'm going to show you how to make a slightly better plot than this. All right, so we're going to be subsetting 2 columns of our data set. It's to avoid spelling mistakes. Okay, and we're going to be plotting it against the pressure. So I just took a vector of column names. Okay, this is an R vector, which is like a list in Python. Okay, and I'm selecting those columns from the NASA data set. All right, so if I just run this, it'll give me, oops, okay, there's a spelling error. Okay, it'll just give me the old plot, but I want to make it better. All right, so how to make it better? Let's give it color. Okay, in this case, okay, sorry, this is what happens when you switch between Python and R all the time. Okay, so you can see the plot became blue. Let me just zoom it a bit. Okay, then we have another argument we can give, which is called PCH. Okay, and this is a number. So what this does is it changes the shape of your data points. Okay, so if I had 25 here, I would get triangles. All right, and so you can look up the entire list on the internet, but essentially it just tells the shape in which we want to signify our data. Then there is another parameter which is called CEX. It tells the size of the markers in our plot. Okay, so we just double it and like I like this better. Okay, then we can give our plot a title, or it's called main. Okay, between displacement and pressure. Okay, I can also give proper labels to my axis. Okay, we will now do oops. Okay, so we have a good plot now. Okay, so I got that off my chest. Let's move on to the actual modeling. Okay, so let's start with a simple linear regression model. We'll build it and then we'll talk about what it means. Okay, what is happening in the model. Alright, so what I've done is I have written, I've created a variable called simple linear model, and I have used the lm function which is built in. Okay, and I'm trying to ask this function, tell me the relationship between pressure with respect to displacement. Okay, so what this gives me is, for the displacement in my data, how does pressure vary? Okay, and I've supplied the data set it's supposed to work with. Okay, so if I now just on this, I will get a formula here. Okay, so this is essentially the same model call that we made, and we get two things over here. Okay, we get an intercept term and we get a displacement. So let's try to understand this. Okay, what happens is, when we have no information, okay, and we are trying to predict something, we typically predict the average value that it takes. Okay, the expected value of the variable. So okay, so this is fairly close. So the point is that the intercept is essentially the model's prediction when no other data is available to it. All right, and so as soon as we get displacement, what will happen is it will adjust its prediction based on the measure of displacement. Okay, so it will multiply displacement with the measured displacement with minus 164. Okay, and it will add it to the intercept. So what we will get is 126.7. okay, suppose displacement was 1. Okay, so this should be the prediction. Okay, so let's test it. Predict simple linear model. So we'll predict using this, and we are gonna do a data frame, okay, that has displacement. To 1. I don't know what. Okay, so we got the exact same thing. All right, so that is how the model found a relationship between displacement and pressure. Okay, the next thing we look at is actually the summary of this model, because that is where the main information is. Okay, so we get this giant text. So let's break this down a little bit and understand what is happening in this case. So this is again the same model call. Okay, it just tells you, it just gives you the command that you use to build this model. Okay, and then we have residuals. Okay, so the idea is that because our data is a scatter plot, we can never, and we are fitting a straight line essentially in linear regression, so the line will never touch every point. Okay, so this is a measure of, on an average, how far away every point lies from the line. Okay, so it's a residual, and what we want here is that in a good model, if our assumptions are correct, the median will be very close to 0. Okay, and the distribution of the quartiles of the residuals should be symmetric. Okay, so as you can see right now, this is fairly symmetric because the line is essentially passing through the center, okay, of our pressure and displacement. Okay, all right, so that's about the residuals, and then what we have here is again the coefficients. Okay, so we already understand what the estimate of the coefficient means. All right, so this is the prediction where no data is available, and we adjust this prediction using the measure of the displacement. All right, then there's this standard error. Okay, so standard error is essentially telling us on an average, okay, when I make a prediction for my my pressure, okay, on an average, how far off is the prediction due to this number. Okay, so because I've chosen this single number, okay, to make predictions for pressure, on an average this number causes an error of 12.86 units, okay, in my prediction. So had this been a different number, because what will happen is this number affects, or it takes the effect of each of these points differently. Okay, so that is the standard error. The t-value is essentially, it tells us how many standard deviations away from the mean is this coefficient. Okay, so okay, and ideally we want this number to be really high. So what is happening here in linear regression is we test a hypothesis. Okay, the result you're looking at is essentially the results of testing the hypothesis that displacement can be used to explain variation in pressure. Okay, so if we know the displacement in the experiment, we can make some prediction about, okay, pressure. And so the exact null hypothesis that we test is that the null hypothesis is that the coefficient of displacement is 0. Okay, which means that whatever value of displacement we have, we will not be able to make useful predictions using those numbers. Okay, so that is the null hypothesis, and essentially, you know, in standard statistics, null hypotheses are rejected at the 0.05 mark. Okay, the p-value, the probability of the data being due to chance. Okay, so here it is way less than 0.05%. okay, so that means that the null hypothesis was rejected, and displacement, okay, the intercept is useful, and so is the displacement in making predictions about, good predictions about pressure in this experiment. Okay, so that is what it means. So we'll see that eventually there will be some features. Okay, so okay, a little bit more terminology. So these are called features, and this is called the target variable. All right, so we are trying to, or many people call it covariates. Okay, some of them call it X, and the other one is Y, depending on, you know, where you learned your linear regression from. Okay, so essentially that is what happens, and few of the features will not be significant. Okay, so in that case, what it is telling us is that, you know, that feature will not add any predictive power to our model. Okay, then we have residual standard errors. Okay, which is essentially a measure of how wrong our predictions are. Okay, how wrong our predictions are, which means, so okay, so when we said we're going to predict, so when we made a prediction of minus 37.36, right, what this number means is that our prediction can be off by plus or minus 6.55. okay, at a 95% confidence interval. Okay, that comes from the rejection threshold, okay, which is 0.05. all right, so at a 95% so confidence interval, we will say that either the prediction is this, okay, or this. So in regression, people make this mistake a lot. They give point predictions, okay? But when you're making a prediction in regression, what you should predict is, your prediction should be an interval, okay, with a confidence level mentioned. That gives, so essentially, because we do not know the right answers, it's a way of saying that this according to our model, the central, the prediction is minus 37.36, but there's a 95% chance that this is not the exact prediction. Okay, no, so we know that this is not the exact prediction, but 95 times out of 100 the prediction will lie between these two numbers. Okay, I hope you got that one. All right, so degrees of freedom is essentially so it's like saying, okay, I'll give you the intuition behind degrees of freedom. So if you toss a coin infinite number of times, based on the counts of heads and tails you get, you can tell if the coin is biased or not. All right, but what if I tell you that you can toss the coin only once? Okay, and based on your reading you have to tell whether the coin is biased or not. Okay, so the thing is, in some sense, the number of instances that we have, right, of our data gives us more confidence. Okay, so yes, in some sense we are determining these parameters, okay, and we will be able to determine these parameters better if we have more degrees of freedom. Okay, and the degrees of freedom is a function of the number of features that we are using and the amount of data we have. Okay, all right, so okay, I jumped a couple of lines. All right, so what happens now is, you can see that the r squared, right, so this is r squared, and then there's this adjusted r squared. What do these numbers mean? They just tell you that the percentage of variation that in your data that your model is able to explain. All right, so this is a measure of the linear relationship between our predictor and predicted variable. All right, and so there's like a 9% linear relation. Okay, so you have to understand that r square in some sense tells you how much better than the mean prediction, okay, your model is doing. So if we had nothing, if we had no features, we would predict the mean. All right, and once we have displacement, we are doing 9% better than those predictions. Okay, that's the meaning of multiple r squared. The adjusted r squared, so the problem with r squared is, if you add more features, it will keep on increasing, and so one might be inclined to think that if you have 100 features, surely we'll reach, we'll be able to explain, or we'll be able to predict all of the pressure variation. Okay, but that is not right, because more data brings more noise along with signal. Okay, and so there's this statistic called adjusted r squared, which accounts for the number of features. Okay, and so essentially your adjusted r square is telling you, all things considered, okay, how much linear prediction power there is in your model on top of the mean. All right, the f statistic comes from the world of ANOVA. Okay, and the goal here is that you will consider your model good if this is far away from 1. All right, and in this case, okay, your p-value, so the p-value here is less than 0.05, and from this f statistic, what you're trying to say is there any predictive power in my model? All right, so the null hypothesis is that this model has no predictive power for explaining variation in pressure. Okay, and so if we are really far off from 1, okay, and we have a p-value which is lesser than 0.05 by convention, we will reject the null hypothesis that this model has no explaining power. Okay, so this model is useful in making prediction. Okay, so this was the very first model. So let's make things more interesting, okay, because we're just using a single feature for making predictions. Now let's build a model which uses all the features. Okay, So there's a couple of ways of specifying such a model. Okay, one is you just type all the feature names. All right, we'll bring this close. So what you do is you specify the equation that you're trying to build. Okay, so explain pressure as a function of frequency and angle. Okay, and the data set to use is NASA data. Okay, and I just run it, and you can see that now I have two coefficients. Okay, but this can get tedious very quickly as soon as you have more than 5 explanatory variables. What if you have 100 of those? Okay, first of all, you should not have 100 features, because okay, that's a separate topic for later. But what will happen is you will dilute your coefficients. Okay, and then you don't know which one was really the main predictor. All right, in some sense. So but okay, back to specifying the model formula. All right, so there's a better way of doing this, which is you just write dot. Okay, and in this case it'll pick up all the other columns from your data that are not pressure, and it'll try to explain pressure using those columns. All right, so we built this model, and then let's look at it. Okay, so we have an intercept term, and then we have a coefficient for every other explanatory variable. Okay, and now we will look at the summary. So what we saw here is, okay, so this is good because we have sort of a symmetric distribution of our residuals, and all of our features are significant. Okay, because we have a p-value less than 0.05, so all of them they contribute to making predictions for explaining pressure variations. Okay, but what is happening here is that we are only explaining 51%, 52% approximately of the variation in pressure. Okay, so it's only rough. Okay, by the way, if you want to learn what these statistical terms mean, I highly recommend a YouTube channel called StatQuest. Okay, I have learned a lot from this channel, and okay, so
hello, I'm Josh Strong.
Okay, so the videos over here give very good explanations of the concepts that we care about. All right, so I watch these videos a lot. Okay, and I learn a lot from them, so I would recommend that if you feel some of my explanations are not great, okay, you can go and look at the visual and theoretical explanations of these things on this channel. Okay, back to models. So okay, now we have this problem where we are only explaining 52% of our pressure variation, and so, or your adjusted R square. So this number varies between 0 and 1. When this number is 1, we are explaining essentially 100% of the variation. Okay, which might be another troublesome issue because we might be overfitting. Okay, that is a discussion for some other time. Okay, but still, when we are trying to build a model, our goal is to push this R squared value as high as possible. All right, and ensure that we are using features that actually have predictive power. Okay, so now what? Okay, what do we do now? So the thing is, there's a few more things we could do. All right, remember our plot. Okay, so if we look at this, you will see that let's look at this. Okay, so for a given setting in chord, okay, the angle sort of doesn't go all over the place. There is some systematic variation in angle and chord. Okay, but those are independent variables, so we'll not look at that. What we will look at is the variable that we are trying to explain. So for essentially, let's look at the chord and pressure. Okay, this is quite clear, or even velocity and pressure. So for various settings of velocity, okay, our pressure has a variation. but you will see that these distributions are not exactly on top of each other. Okay, there's a certain confined space that the observations occupy. Okay, and none of the observations for this velocity settings in pressure go all the way till here. Okay, so this particular setting of velocity has its own region, okay, where the pressure will vary, and a different velocity setting now actually causes a slight different behavior in the pressure distribution. All right, so we want to model for this. Right now what we are doing is we are essentially drawing a line that fits best in these four distributions. And so what I want to introduce now is something called as interaction effects. Okay, so where I want to model pressure variation specifically for this setting of velocity. Okay, and then the model should account for other settings of velocity, okay, in a little bit more nuanced way than just taking, essentially right now it's taking the average of, in some sense it's taking the average making the prediction for average velocity. Okay, so now let's actually do an interaction model. Okay, so I'm gonna type it. In fact, let's type it. So let's make a simple interaction model. Okay, so we're going to explain pressure with chord and velocity, and we're gonna see how the presence of different settings of chord affect different settings. Okay, for a given chord setting, and if we change velocity, so we fix chord and we change velocity. Okay, if we account for this, how can we get better predictions? Okay, that is the goal. Just grab it. Okay, all right, so okay, so let's build this model. Okay, all right, so what we have now is how, let's try to interpret this. Okay, so when we have the measure for chord and velocity, okay, and we are trying to predict pressure, what it will do is it will not only substitute the measurement of chord and multiply it by minus 14.43, okay, add that to the intercept, and then it will take the measure of the velocity, okay, and add that to the intercept. Okay, so this is going to adjust the prediction in the downward direction, and this will adjust the prediction in upward fashion. All right, now this one, what it will do is it's going to multiply the, okay, so it's going to do either of the two things which are equivalent. Okay, it's going to take the current measure of velocity, okay, so it's going to pick up this coefficient, okay, and it is going to add it to the product of the chord coefficient and this. Okay, wait, no, that was wrong. Okay, so it's gonna take the measure of velocity and multiply it with this, and it's going to add the coefficient for chord. I'm going to verify this. Okay, so this is a good explanation on interaction effects and their usage. Okay, so here they are comparing the effect of sales for the amount of money you spend on YouTube and Facebook ads. Okay, so let's look at this. All right, so what it is doing is the same thing. Okay, so these two are equivalent terms because we are looking at a two-way interaction. By the way, we can make multiple level interactions, but that is usually not recommended because it makes models unnecessarily complicated to interpret, and they are not sparse models. Okay, and it's always best to have a simple model than a more complicated one. So what is happening is, in our interaction term, okay, so let's look at the coefficients. Okay, so this is the coefficient over here is b1, b2, Okay, sorry, that's the intercept. B1, B2, B3. Okay, so YouTube, Facebook, and the interaction. So what is happening right now is it's taking the Facebook coefficient and it is taking the plus the interaction of Facebook, the interaction coefficient multiplied by the YouTube marketing spend. Okay, and it's multiplying it with the spend. So in our case, what will happen is it'll take the chord, okay, and it will multiply it with the third coefficient where we have the chord velocity interaction, and it will add the velocity coefficient. All right, let's look at the screen. Okay, so what it's gonna do is it's gonna take the measurement of the chord that we supply for prediction with this, okay, and it will add this coefficient. Okay, now this will go into the prediction apart from the multiplication of chord measure with its coefficient and velocity measure with its coefficient. All right, so it's essentially trying to simultaneously consider the effect of velocity and chord for a given measurement. So in principle, what you can do is you can pick either one of these chord or velocity measurements, multiply it with this, okay, and add the coefficient of the other variable, okay, to make your interaction effect prediction. Let's look at the summary. Okay, so in this case we notice that actually the null hypothesis that the interaction has a predictive value has been rejected, because this is not a significant variable, okay, this interaction. So, and we can also see that because this coefficient is really close to 0, sometimes that is not the case, okay, and that is why we need a statistical test to get that. Okay, so all right, so now let's actually again address the issue that we addressed here. What if there's a lot of variables and I don't want to go on typing all this? So there's a shortcut for specifying two-way interactions, which is this. This is going to use everything in my data set. Okay, this is the convention for that, and it's going to do two-way interactions. Okay, if I made it 3, it would have done 3-way interactions, but we generally not a good idea to do 3-way interactions unless you have very good domain knowledge about the problem you're trying to solve. Okay, so let's look at the results. All right, so what you can see is there is a lot of coefficients that got generated. Okay, which is, it's taking individual predictors, their coefficients, okay, and then a bunch of interactions. Now the thing is, a few of them are not useful, right? And ideally you would not want to include these in your model. You only want significant features, and we have sort of using interactions started pushing our R-squared, but our adjusted R-squared should get better if we reduce the number of features, okay, because these are useless features. So how to do that, right? Because number of features can actually go into several, okay, and then their interactions will also increase the amount of coefficients that we calculate. So one way of doing this is to automate your feature selection, okay, and that is done through, we're going to import the library called MOS, okay, and this has something known as a stepwise regression implemented. Okay, so what it does is it essentially starts from 0 number of features and it keeps adding features, okay, and looking at how good the model is. And then actually let's just implement it first. Okay, did I import it? I have to import it. Okay, stepwise model. And all we do is we take the model that we built, okay, and we pass it in. That's it. I think that is it, and it will automatically select features for us. Okay, it's so it's basically reducing these features, okay, and it's telling us, so a lower AIC is better, and it's trying to find the AIC is an information criteria. You should look it up. Okay. So it does several iterations. It actually starts from a full-fledged model, decreases the features, and then it starts from a 0 feature model and increases the features. Okay, I think I can, yes. So you can do either a forward, I hope that works, okay, or you can do a backward. But what I typically do is I do both. Okay, and this gives the best model. So let's look at the summary of the stepwise model. Alright, so we are now pushing our R squared to 63. Okay, and all our features, okay, some of them are still not good, but the interactions are good. Okay, that is why we have kept them, otherwise it would have eliminated. Okay, so individually this makes sense, because individually these features did not have any predictive power. You could just draw straight lines through or a horizontal line. Okay, but now you can see the value of interaction, that as soon as we start looking at combination of features instances, our prediction sort of gains. Okay, we have adjusted R square of 63, and before this we had 63. Okay, so it's the same model, all right, with these features being disregarded. Okay, but we have come from 6%, so that's not bad, just by adding interactions. Okay, but wait, there's more. Okay, so we can do few more things. So now what happens is, for this we have to understand or know some of the assumptions that linear regression makes. Okay, it assumes your data is normally distributed, each instance is independent from each other. Okay, the IID assumption, and these models work best. So another pitfall in linear regression is that if your frequency is in the order of megahertz, okay, that's millions, this number will hugely affect the output. Okay, just because it is a large number, so the coefficient associated with it will be really small. Okay, and so that has the danger that a really small coefficient for a value that can take like the value in millions is that we may not be able to reject our null hypothesis, because the coefficient comes out to be really small, even though there's some predictive power. And so what we do is we level the playing field for every feature. Okay, and the way that is done is you essentially scale. Okay, you scale the features. Okay, so let's try to do that. Okay, so there's a function called scale. Okay, and I can choose, let's actually first do a histogram. Okay, let's do a histogram of frequency. Okay, you can see this frequency is distributed in this huge cube. Okay, so this is just a frequency. This is a frequency plot of a frequency. Okay, it's a frequency distribution of frequency. Okay, it just tells me that most of my observations are in this range. Okay, be about 2000. Yes, so 0 to 2000. I have most of my observations, a little more than 800. Okay, but what if I now? Okay. So this, let's scale this. Okay, so once we scale it, we have two options that we can do. We can center it, okay, and we can what else can we do? We can center it and we can scale it. Okay, so scaling it, okay, that was obvious. Let's do it one thing at a time. Okay, so these are booleans. Okay, so, and let's plot it. Okay, so what we see now is that this is now centered around 0. Okay, so we sort of modified the numbers. Okay, so these numbers have now been changed in such a way that the data that was at the center of all the observations is now considered 0, okay, and everything below it is a new number, okay. But okay, this will make more sense if we do this. Okay, this is the level playing field I was calling you. Okay, so what it is doing is it is scaling everything based on standard deviations. Okay, so this value is 5 standard deviations away from the mean of the frequency. All right, and this is where you want to go back to StatQuest and look how standard deviations are measured. Okay, what exactly is the significance of standard deviations? It's essentially creating a level playing field for, so I can scale any variable based on its standard deviation, okay, and it'll range, and its central tendency will be 0, and it'll basically now measure in terms of number of standard deviations, and the exact value will not be used. Okay, so we are now sort of scaling it on a normal distribution. So we assume that the data was normally distributed, and that is why we can do these things. Okay, so let's apply it. Okay, so what we are going to do is we are going to apply it to all the columns of our data, and that is where the apply function comes in. Okay, now it's our data, and we are going to only use the features that we use for prediction, okay, which is these 5, and we're going to say that, hey, just because you have some of these have a high magnitude, they don't get to affect our predictions disproportionately by virtue of their magnitude. Okay, so we level the playing field for all of them. So right now I've chosen the subset, okay, of data. Then I'm gonna, the second argument is 2. Okay, so this is essentially, if it was 1, we write a function here. Okay, and so this function will be applied to this data frame column wise if this is 2, and if this was 1, then the same function would be applied row wise. All right, and okay, so we will now, I don't want to use this, I'll use the statically specify function. Okay, function x. So it's gonna basically put the x right now when this function is being run will be the column. Okay, and everything inside this will be what happens to the column. Okay, so we're gonna scale x by centering it and scaling it. Okay, what is wrong? Okay, that was not right. Okay, I think so. Right now what we'll do is we will look at the head of this. Okay, so we have still not modified our data. We are looking at what it will look like. Okay, so now everything is close to 1 and minus 1s. All right, so this is what will happen to our data now. Okay, so modified scaled NASA data, okay, is going to be this. Okay, I missed this. So 2 things I missed. Okay, first we have to create a copy of NASA data. Okay, and then we're going to modify these columns. Okay, and those modified things is what we are going to assign. Okay, this is getting dirty. Maybe this will be better. Okay, anyway, I hope this works. Oh, it worked. And that is why, folks, you should write clean code so that you don't yell at yourself a couple of months after writing it. Okay, so now we have, let's view it. Okay, So I have kept my pressure measurements, but now everything else is centered and scaled. All right, this is what we will use to now build our stepwise interaction models. Okay, I'm gonna use shorter names now. Stepwise scaled data interaction model. Okay, before that we have to now do a scale data interaction model. Okay, which is pressure as a function of every two-way interaction for scale NASA data. Okay, and so we have not improved our adjusted R squared. Okay, but we will still try to improve things. All right. No, there's not a whole lot of improvement. Okay, but this was important to tell. Okay, now the other thing that we could have done, okay, and I'm gonna try that, is instead of scaling these things, notice that in our plot, there were distinct levels for some of the features, right? And so let's actually categorize them. Okay, we will consider them distinct factors instead of numbers. Okay, so, and that will help me also explain what happens to categorical data. Okay, once we have categorical data, the way the regression model is built changes. All right, so let's convert velocity, because it has distinct variations. Okay, chord and angle. So we're going to convert angle, chord, velocity into factors. Okay, they will no longer be numbers, which means we cannot scale them. All right, so now it will be mixed type. So data is first of all a copy of NASA data. Okay, let's view it. To ensure it is a copy. Yeah, it is a copy. Okay, now we're gonna use the apply function. Okay, again, okay, I'm gonna write it from scratch. So now first we choose the columns. Okay, we'll call them factor columns. Is a vector of velocity, chord, what was the other thing again? Angle. Okay, and then we'll say mixed type. Now sorry, it does every row which has, but only the fact columns will now be subjected to along the column to a function that converts the column into a factor. Okay, this is where now our mixed type str comes into play. Okay, so now we can, oops, hey, I did a mistake. Okay, what was it? Data frame, mixed type data, fact call not, oh, we had to declare this. Okay, so now let's look at the structure. Okay, So now these columns have become characters. Okay, I wonder why that happened. Should have been factored. Either way, it will not affect our results because they will be interpreted as different levels instead of numbers now. Okay, and that is the point we are trying to make. So now we're going to make a simple we're going to make a mixed data linear model, and I will tell you in a bit why we didn't go for the fancy interaction effects. Okay, pressure as a function of everything. So mixed diagonals are right. Okay, let's hope. Okay, cool, this worked. And what just happened? Why do we have so many coefficients? Okay, and that's why we didn't use interaction terms. Okay, so let's spend some time interpreting this. What is happening is, you know, as always, our intercept is being measured, okay, or calculated, and then for then angle, right? Angle itself has a let's see. Okay, if we look at unique, we have about a lot of levels. All right, so now each of these is not a number anymore. Okay, it's a distinct level for which the coefficients are being calculated. So what happens is, for the 0, so you will notice for which angle, okay, well, we should go all the way to 50. Yeah, okay, so for which measure of the angle, you will see that the name of the column has been concatenated with the level. Okay, it's no more a measurement, it's a distinct level. So we'll see that coefficients for every level have been calculated except the 0. Okay, that is because the coefficient for 0 goes into our intercept. Okay, so what happens is, if our angle is 0, then none of these features will be used for prediction. Okay, but if the angle is not 0, suppose it's 1.5, then this coefficient is the one that will go into making the prediction for pressure. Okay, and so essentially one of these coefficients will be picked up if the angle is not 0. Okay, so and that is why every level now gets equal importance in making the model. Okay, same thing with the chord. Okay, every setting of the chord has its own. So this is another way of sort of modeling interactions. Okay, because but this is possible only in cases where you have a low number of levels. Okay, this will get fairly non-parsimonious as soon as we have many levels in our data. Okay, so that is a judgment call we have to always make while building models, and this is not exactly the best model we have built so far. Okay, so let's try to see if we can stepwise mixed data model. Okay, and if you look at the model call, seems like there are fewer coefficients. Okay, and okay, still decided to keep these. You have to keep these because you cannot ignore a specific level. Okay, so that is another drawback. And we did 55.48, and right now we are at, okay, we didn't improve our R squared. But okay, so now we know a bunch of ways in which we can build models. Alright, so this is all I had for today. Hopefully see you in the next video.